Okay. So equilibrium. We talked about this a little bit yesterday. When we talked about a weak acid. So remember, in equilibrium, let's say we take compound A and react it with B, and let's say we form compound C. Okay. What equilibrium basically implies is that most reactions in nature don't actually just go and form our compound C and it's done. What it does is A and B start off and start forming C, and then eventually at a certain point, let's say C plus B, it forms C and B, and then at a certain point, C and B start reacting with each other and reform A and B. And then A and B then form CB, and you kind of get the cycle. And when the rate of the forward reaction is equal to the rate of the reverse reaction, we are said to be called an equilibrium. Okay, so a system in which both forward and the reverse process are occurring at the same rate is called equilibrium. Okay, and this just kind of shows a picture of this. So they don't show the chemical reaction. There it is. N2. Let's put it here. They're on a different page. N2O4 forms NO2. Okay, so they're showing at time 0, 100. Let's put this as a percentage. 100% of our mixture is the N2O4. Okay, and 0% of it is our product. Okay, and then eventually it starts reacting, and so our concentration of our, let's put here N2O4, it starts going down, and the concentration of our product, or NO2, starts increasing. So that starts increasing, that decreases, and then at a certain point, when you form a certain concentration of NO2, all right, whatever that concentration is, let's say it's 60%, and we have a certain concentration of N2O4, let's say it's 40%, once it hits this amount, so once I get 60% of it as NO2 and 40% of it of N2O4, the NO2 starts reforming N2O4. And then the N2O4 starts forming the NO2 at the same rate. So that's basically what this graph is showing you. All right, and then they're showing you a picture here. Okay, well, we can figure out what this value is. I think it should be balanced. It should have a 2 here. We can figure out what that number is, or that value. So it's what's called an equilibrium constant. It's basically a number that tells you how much of your product there is with respect to your starting material. Okay, so they don't actually show it to you. I don't know why the slides aren't showing to you. So what you basically do is your K equals the concentration of your products divided by the concentration of your reactants. Okay, so it's the concentration of this, all right, divided by the concentration of the reactants. Kayla got booted. Oh, her internet shut off. She's like, oh, okay. That's okay. I'm recording it. Okay. Now, all depending on, and then when you have so here it shows you the equilibrium constant. Okay, so our products is NO2, so it's the concentration of NO2, and it's all divided by the concentration of our reactant. All depending on our balanced value, you put that as an exponent. Okay, so since there are 2 NO2s, you've got to square that concentration of NO2. All right, so that's basically how you do an equilibrium constant. It's the products divided by the reactants, and whatever our balanced equations are, you raise it up to that power. All right, so here are just a few practice problems. All right, so just to do the first one real quick, our K, our KEQ, however you want to call it. I think they just call it K. Yeah, it's either K or it could be called a KEQ for an equilibrium constant. Would be the concentration of ammonia squared. Sorry about that. Yeah, this thing does that all the time. I don't know why. squared divided by the concentration of N2 by H2 cubed. All right, let me see what you said. Can you say that one more time, the definition for the equilibrium constant? Here, let's just look at the slide. The product and product's concentration, each raised to its coefficient in the balanced equation divided by the product concentration, each raised. Yeah, it doesn't. It's basically just showing you the extent at which, how much product you have versus how much reactant you have. When we actually look at the values, I'll kind of explain what the value is. So yeah, I didn't really say it too much, just because I'm going to talk about it a little bit more later. But it will make sense. So it basically shows you the extent of how much product you have. Like for example, if I have a KEQ equal to like 100, all right, that means I have 100 times more product than I do my starting materials. All right, that's kind of what that tells you, right? Because if it's 100, it's 100 over 1. So it means that my product is 100 times the amount of concentration as our reactants. If I have a KEQ of like 0.1, all right, that means I have much more reactants than I do of my product in the reaction. So the equilibrium favors more of the reactant side than it does of the product side, right? It's basically telling me that there are 10 times the amount more of my reactants, right? Because if I have a small value, so a KEQ less than 1 implies that my denominator is much larger than our numerator. So it means that these concentrations are much higher. Does that make sense? It's kind of a mathematical way of talking about it. So that's basically what these numbers imply. Okay, so why don't you go ahead and do the KEQ for, let's do like B and F. All right, I'll put this on pause. You guys can go ahead and let me know when you guys are ready. Okay, so let's go over these. So for B, so what you do is, the pyramid just showed up. I'm going to have to slip up. Okay, Mike, that's all right, no problem. All right, so the KEQ, so it's the product, which is HI, divided, and you square it, because it's 2, and then it's times the concentration of what your hydrogen is and the concentration of your iodine. So that would be the KEQ for B. Now, as far as the values, we aren't giving it any values, but I believe in the next few slides, I'm sure they'll have values there. And then we'll plug them in and we'll get a number. But this is just showing the actual equation. All right, NO2 squared divided by NO squared times O2. Okay? Any questions on those?
So, I'm sorry, did we just leave it like that?
Yeah, for right now. Yeah, as soon as we get values, then we'll plug the values in. But
okay.
But as far as equilibrium constant, that's what the constant is. And then once you're given values, you just plug them into here and solve for it. Yep.
Okay.
Yep.
You said that's what the constant is?
The equilibrium constant.
Okay.
Yep. Okay. So let's just give you the answer. Okay, so here's actually a problem where they actually have values. All right. So in a case like this, I'll just go through the slide. I don't have to do it, but it's basically so your equilibrium constant, or I think the book calls an equilibrium expression. Oh no, right here, an equilibrium constant. Here you go. So it's your COCl2 divided by the concentration of your chlorine divided by the concentration of CO. So the concentration of COCl2 is 0.14, so you just plug that into there. And everything is a 1-to-1. I don't think I need to balance this. Yeah, everything's a 1-to-1. And then it's divided by your chlorine concentration, 0.054, and then by the concentration of your CO, which is 1.2 times 10 to the negative 2. All right, so here it is, and you get 216 as the equilibrium constant. So, I don't know if your book talks about, yeah, your book kind of talks about it, but I'll talk about it here. Okay, so the question is, what does this number mean? Now, there are no units here. This number basically tells you how much more one side of the equation favors the reaction. Okay, now remember, this is in equilibrium. Okay, it's not that 50% of it is always product and 50% of it is always reactant. Every reaction has a different amount of what it favors. And remember, our equilibrium constant is our products over our reactants. So if this number, if our KEQ is greater than 1, that implies that our numerator, all right, up here, is larger than our denominator. All right, in math, if your number is greater than 1, it means that the top number is larger than our bottom number. Okay, so if you look at it, the product is larger than how much of the reactants you have. If your KEQ is less than 1, that means your reactants, you have a lot more concentration of your reactants than you do of your products. Okay, so I'm trying to give you a visual. So if you're greater than 1, that means that the equilibrium favors the product side. That means I have 2,016 times more of this concentration than I do of my starting materials. Does that make sense? And then
2,100.
I'm sorry, it's 216.
Okay.
Yeah, did I say 1,000? I meant 16. Sorry about that. All right, so it means that it's 216 times more of the COCl2 than I do have of the CO and the Cl2. All right, if my value for some reason, if my KEQ was like 0.001, obviously that means I have a lot more of the reactant than I do of the product. So is that 1, 2, 3? I have 1,000 times more of my reactant than I do of my product. So that's kind of what this value implies. It basically shows you which side of the equilibrium it favors. Okay, so a very large number means it favors the product side. It means that I have a very small amount of the reactant once it hits equilibrium. It's basically, it's forming. If we actually go back to this slide, this one here, these lines would be more like this line would be like up here. So this is my product. And my reactant, I still have a little bit of it, but it'll be way down here. That'll be my reactant. Okay? And obviously, if I had a 60-40, it would look like this. If I had exactly a 50-50, I would have here, and then this one would be exactly on top of it. So it's not like I always have a 50-50. It just all depends on the reaction. Okay? And that's basically all an equilibrium constant implies. Okay, now in here they talk about if it's 100 more or not, but I'm not going to go with that. But basically, when magnitude K is very large, the reaction will go essentially to completion, and the equilibrium mixture will consist predominantly of the products. Okay, so a large, if it's greater than 1, means I have a lot more products than I do of the reactants. And then the opposite is true. If the magnitude is small, the equilibrium is predominantly the reactants. It means that the reaction doesn't really go that much, and I have a lot more of this. There's a lot of reactions in our bodies that actually don't go, or the equilibrium constants are very, very small. So that's why we need enzymes in order to act as a catalyst, in order to catalyze our reactions. Most reactions in our natural environment actually are in equilibrium, and they actually favor the reactant side. They actually need a catalyst in order to get it to go. Okay? Does that make sense? Talk about other factors. But that's basically how you figure out an equilibrium constant and how you do it.
Oh, that's just in scientific format.
Yeah. Scientific notation. Will this stuff be? Yes, it will be. Let me see something. Okay, I just wanted to see the. I didn't miss anything. Okay, so now let's talk about factors that affect the equilibrium. Okay, so just because I have an equilibrium, how do I make a reaction go? I'll show you a perfect example. If you take ammonia, if you take nitrogen and react it with ammonia, if you take nitrogen and react it with hydrogen, you form ammonia. Okay, and I think we would have to put a 3 right there. Okay, so that's the balance equation. All right, so this reaction is a major equilibrium, and it actually favors the nitrogen and the hydrogen side of it. Okay, however, ammonia, we use tons and tons, like millions and millions of tons of ammonia in our society for farming. All right, so for soil, ammonium nitrate is used, but it comes from ammonia. So the process of making ammonia is very important. You need a cost-effective way, and you have to be able to make lots of it. All right, and it wasn't until I think like about 100 years ago there was a scientist. His name was Haber. This is called the Haber process, in which he found a very easy way in order to make tons and tons of ammonia. Okay, however, how do you make a lot of ammonia if you mix these and in the equilibrium you only make a very small amount of it? Okay, well, he used something called the Châtelier's principle. All right, and what Châtelier's principle is, if you stress this reaction a certain way, you can actually shift the equilibrium whichever way that you want it to go. So if you want to form more ammonia, there are things that you can do in order to force it in order to go that way. If you want to slow down the process of the formation of ammonia and stop making ammonia, there are ways that you could shift the equilibrium that way and not make any more ammonia, and you start making all the nitrogen and hydrogen. And Le Châtelier, he discovered this principle. This was before Haber. Haber just used this principle in order to make ammonia. Okay, so when a stress is applied onto an equilibrium, all right, the system will respond by shifting in the direction that minimizes the effect of the stress. All right, in this context, stress refers to a disturbance in the force at equilibrium. I just had to say that. At equilibrium by any of the following means. All right. So basically, this is what Le Châtelier's principle is. You can kind of think of this as like a seesaw, like a kid's toy at a park. All right. Basically, what happens is when you reach equilibrium, you have a certain amount of our reactants and you have a certain amount of our products. Once we have established those amounts, we are in equilibrium. Okay. Now, if we were to do something like increase the concentration of nitrogen, if I were to increase our concentration of nitrogen, so all of a sudden I put tons and tons of nitrogen in here. All right, I have changed our equilibrium. Our system now has a lot more nitrogen in it than what it should have at equilibrium. So our reaction responds by removing that extra nitrogen and trying to establish equilibrium on that nitrogen. So what's going to happen? That extra nitrogen is going to start reacting with hydrogen and start forming more of my ammonia until I establish equilibrium now based on the fact that I've just increased my amount of nitrogen. Okay? If I decrease the amount of nitrogen, let's say now if I remove nitrogen from here, what's going to happen? Well, I now have a hole on this side. I now, I'll technically have a lot more ammonia than I do of my reactants. So my system is going to try to replace that amount of nitrogen I removed by breaking down the ammonia and shifting the equilibrium that way now in order to fill up that empty spot. Okay, so our reactions are constantly moving, and its main goal is to establish equilibrium. So if I were to change any of the concentrations, all right, I can shift it one way or the other. Okay, so what Haber, what he found out is that ammonia, it turns into a liquid at a much higher temperature than our nitrogen and our hydrogen. All right. So what he did is he has a reaction vessel, a huge reaction vessel. All right, that looks like this. All right, and in coming here in the top is all of the nitrogen and hydrogen. Okay, and he's constantly is pumping in nitrogen and hydrogen. So these concentrations are incredibly high. All right, he's constantly increasing our nitrogen and hydrogen. He also has cooled this down so that once the ammonia forms, it turns into a liquid. Once something is a liquid, it's no longer in the equilibrium. It has to stay in a gas phase. Okay, so he cools it down enough where it turns ammonia into a liquid, but it keeps these as a gas. So what's happening? The ammonia is liquefying at the bottom, and the ammonia liquid is being removed out of the tank. And the nitrogen and the hydrogen are being pumped in here, and they technically are never establishing equilibrium because the ammonia is constantly being removed out of the equilibrium. So you never have ammonia in here to reform the nitrogen and the hydrogen. It's just basically our nitrogen and hydrogen are constantly reacting, and as soon as it forms ammonia, it liquefies and gets removed. So I never have ammonia in here. It's basically all the nitrogen and hydrogen. And that is basically what the Haber process is, how they can make tons and tons of this stuff every single day very quickly and all cheaply. So here, again, it shows you the addition of a reactant or product. It changes it. So I showed you if you increase our concentrations. If you decrease our concentration, so that's basically what I'm doing here. I'm decreasing our ammonia concentration. They also talk about like the volume and stuff like that. I'm not going to go into that stuff. And then in the temperature, I showed you how it can change with our temperature. If you liquefy one of them, you technically are removing it. Okay, so in this case, it'd be said that we're shifting the equilibrium towards the product side, our product side, because I'm shifting it that way. Okay. I think they talk about the Haber process here a little bit. Here they talk about the equilibrium. So if you notice that the original equilibrium is 0.297, so that implies that the equilibrium favors our reactant side, the side of the hydrogen and our nitrogen, because that value is less than 1. So it means I'm larger on the bottom. Here is when you add a little bit of nitrogen to it, notice that the equilibrium shifts. Okay, and then eventually it will establish equilibrium. Okay, so again, it's basically everything I talked about. If you add nitrogen, if you add hydrogen, and you remove ammonia, notice the equilibrium that the arrow is going towards our product side. If I did the opposite, if I added ammonia into here, so let's say the reaction that got out of control is going way too fast. All right, if you start adding ammonia into it, it'll actually start going backwards and start reforming nitrogen and hydrogen. All right, so here I'm removing these, or if I'm adding ammonia. Okay. Okay, so an industrial important reaction for the production of hydrogen gas is called the water-gas shift reaction. I did not know this, so here you go. You take carbon monoxide, add it to water, and you can form CO2. So this is a way to form CO2 and hydrogen gas. I guess hydrogen gas is the one that's important. For each of the following scenarios, determine whether the equilibrium will shift to the right, the left, or it won't shift at all. Okay, so if I add CO So I'm increasing this. You guys tell me which way is the equilibrium shifting. Is it shifting towards the right, which is the product side? Is it shifting to the left, which is the reactant side, right? If I'm going towards the right, I'm going to the product. If I go to the left, it's the reactant. Or does it have no effect at all? What do you guys think? Why don't you put either R, L, or N in the chat box? So if I increase CO, what do you guys think? Which way is the equilibrium shifting? The right. That's correct. Holly says the left. All right. It's going to the product side. It's going to the right. If I put more CO in here, that means I have a lot more reactant. All right, and the equilibrium has to remove that excess CO that I just added in there. Okay. Anytime I have an overflow of an amount. All right, the reaction has to compensate for that increase by reacting it out of the reaction and forming our products. Okay, so I think I said earlier, it's kind of like a seesaw. Okay, so if you remember a seesaw, oh, that's a bad seesaw. So a seesaw, remember, and I have the fulcrum here. I have a person there and a person there. All right, if this side is up, my left side, if I increase my concentration, what's going to happen to the seesaw? This has to go up. That goes up. So if I increase this side, what happens is the equilibrium shifts towards the right in order to increase the concentration of my products. I don't know if this helps or not, but this is kind of how I see a seesaw. And again, I'm trying to get equal. I'm trying to get level. So if this side is going up, right, after it's up, it has to balance itself out by increasing this side of it, our product side, or the right side. Okay? Does that make sense? So if I increase my CO, I have to compensate for that increase of concentration. I got to react it out of the reaction. It's way too high, so water starts reacting with all of that extra CO in order to establish equilibrium again, and it shifts towards the right. Okay? Does that make sense? So if we were to, okay, good. So if we were to remove water, okay, so let's say now I removed water. I'm taking water out of the reaction. Which way is it going to shift? Is it going to shift to the left, to the right, or does it have no effect? The left. Perfect. You guys got it. Exactly. I now have a deficit of water. So the reaction has to reform that concentration. So these have to start reacting and start reforming water. So again, on our seesaw example, it would be that my reactant side is lower. So here's my reactant side. Here's my product side. Product. So this is lower. So in order to establish it, I have to bring this down. My concentration of my reactants have to go down because I have to increase the concentration of my product. I'm sorry, the products are going down. I have to decrease my product side, increase my reactant side. Exactly. So I have to increase this. In order to increase this, these have to react and start forming my reactants. All right. How about the removal of hydrogen? So I do the reaction and I remove hydrogen. Let's see if I can erase some of this. This is getting real crazy in here. There we go. I like the eraser better in this, but I like writing in the other thing better. So I remove hydrogen. You guys, okay. So Kimberly says it shifts to the right. That is correct. I now have a deficit of hydrogen. The equilibrium has to replace that loss of hydrogen. So in order to do that, my reactants have to react and shift to the right or the product side and start establishing that home. And then how about if I add carbon dioxide into here? Which way is it going to shift? Left. Correct. I have too much of this now. So I have to react it away and start forming more of my reactants. Good. You got it. You guys understand the Châtelier's principle. And this principle is a pretty important principle in biological systems. If you go off and take organic chemistry or biochemistry, this principle is pretty important. They talk about it quite a bit. Because in our bodies, what happens is we have a mechanism. If we have a reaction that's going on in our bodies, it doesn't just keep going and produce a certain hormone or something. Our body has a way to actually shut off a system that will produce a certain hormone. It's not like our bodies just constantly make the hormone. Once we get way too much of it, our bodies have a mechanism, in order to tell the reaction, all right, you have to stop because I have way too much of a compound. Well, it's based off of Le Châtelier's principle. If I'm starting to form way too much of a hormone, all right, and my body only is able to hold a certain amount of it, once I get way too much of this, it starts either reversing back and form our starting materials, or it has a system in order to shut this off until I consume that hormone, and then it turns back on again. So most of the reactions in our bodies are based off of this Le Châtelier's principle.
How do you spell Châtelier?
It's French. It's Le Châtelier. Yeah. There you go. Voilà, Le Châtelier.
One of the factors that affect equilibrium.
Yes. All right, so here is kind of a problem where they give you the equilibrium constant, where you kind of have to figure out. I think all these are in the wrong spot. Should be able 2 there, 2 there, and 2 there. I think they put them up. They said begin writing the expression, and then the addition. I think we just did that problem. There's that one there. Okay. All right, the volume, I'm not going to talk about that. Don't worry about that. Heat is kind of a factor. You kind of treat heat as if it was like a reactant. Okay, so all depending on the side. Okay, so here is an endothermic reaction. If this reaction requires heat, if I were to heat this reaction up, which way would the equilibrium go? Would it go to the right to form the product? So we'll put R. Or will the equilibrium go to the left? If I were to increase my heat here, if I were to make it hotter, the right. Yep, exactly. Right. So if I were to increase this, if I heat up the reaction, it'll favor the product side, or the right. Exactly. And if it was an exothermic reaction, if I had heat on this side, let's say, and I made the reaction cooler, I cooled it down, which way would it favor? If I cooled down the reaction. I think Kim said the right. I don't know if that was from the last problem or this one. I think it was this one. Yep. Yes, exactly. So if I were to cool this down, that means my heat is going down. So the reaction has to replace that loss of heat. So we have to shift that way. Yep, got it. Perfect. Here's actually showing you a chemical experiment that kind of shows that that you have a reaction, and by heating it, it turns into a different color. This makes no sense if you don't understand that. But. Okay, so that's pretty much it for this chapter. So it's basically equilibrium constants, understanding what an equilibrium constant is, how to figure it out, how to put in values into it and solve it, and then Le Châtelier's principle. Okay, so any other questions?